Hey there, Ravens. Time for Atomic Theory Part 3, talking about Rutherford's gold foil experiment. Alright, so Sir Ernest Rutherford was credited with discovering the nucleus in 1911. And later on, he discovered that the nucleus was made of protons and neutrons with his counterpart Chadwick. We'll talk about that at the end of this session. Alright, so let's look at his experimental apparatus, the tests that he did. He had a lead block, and inside this lead block he placed some uranium. Uranium is radioactive, so it produces alpha particles naturally through radioactive decay. These positively charged alpha particles, he created just a tiny hole inside this lead box so that the alpha particles had only one way to go out, thus creating a beam of alpha particles. These alpha particles were shot through a very thin piece of gold foil, and surrounding that gold foil was a fluorescent screen that would fluoresce, and they'd be able to detect if the alpha particles touched the fluorescent screen. Okay, so the accepted model of the atom at the time was Thomson's plum pudding model, where the atom has negative particles within a matrix of that cookie, that plum pudding, which was positively charged. So the positive charges are all spread out throughout the atom, and you had the negative charges scattered throughout that then balanced the atom. So remember, the atom was neutral and everything was evenly spaced. So Rutherford expected that if the positive charges spread out throughout the atom and you throw positively charged alpha particles fired through it, then the alpha particles should pass straight through without any change. Okay, so here's what it would look like. He said the alpha particles, boom, would shoot straight through, come out the other end, nothing exciting at all. What actually happened, though, looks like this. Oh, I'm sorry, let's explain first. Because he thought the mass, cool graphics, I know, the mass and the positive charge was evenly distributed, the alpha particles wouldn't be repelled, they would just pass straight on through. Alright, so here's what actually happened. Okay, most would go through, but some got deflected back. Let's take a close-up look and see exactly what really happened, what it appeared to look like. Here's how he explained what was happening. The atom is really mostly empty space. There's a very small, dense, positively charged center, and the alpha particles are deflected by this positive charge if they come close enough. Okay, so those are the alpha particles, and when they come near that positively charged center, they're deflected. They bounce back, they bounce off, okay? But they get detoured. Alright, so what did his model then look like? He revised the model of the atom and said that there is this positively charged, very dense nucleus in the center, and that those negative particles are able to fly around on the outside. Alright, movie time.
The mystery of how the electrons fitted inside the atom was eventually solved here in Manchester, in this building in 1911, by Ernest Rutherford. Rutherford was, in my opinion, one of the first proper particle physicists because he used beams of particles as projectiles to explore the structure of matter. Now, of course, in Rutherford's day, there was no such thing as a particle accelerator. So he used the decay of radioactive elements to produce his beams of particles. This is Rutherford's original desk. And in fact, if you hunt around a little bit, you can detect traces of radioactivity 100 years later. Rutherford asked two of his students, Hans Geiger and Ernest Marsden, to fire some alpha particles at a piece of thin gold foil. See what happened. So Imagine these tennis balls are the alpha particles. Now, if the atom were, as Thomson had suggested, a kind of amorphous blob, then you'd expect the alpha particles to pass right through. And that's indeed what happened to most of them. But to their surprise, they found that around 1 in 8,000 bounced right back. After 2 years of puzzling over the meaning of these results, Rutherford realised that in order for the alpha particles to bounce back, they must hit something small and dense. So his new model of the atom was a bit like the solar system, with all the mass concentrated at the centre and the electrons orbiting like planets around the sun.
Today, we know that this picture isn't quite correct. Quantum mechanics tells us that we can't know precisely where the electrons are, but we can predict that they reside in distinct shells around the nucleus.
Rutherford's alpha particle scattering experiment was remarkably direct and simple, and it showed the nature of what the atomic structure is. By the way the alpha particles bounce off the atom, he worked out where the positive charge of the atom lives.
Rutherford had come to the astonishing conclusion that most of the atom, and therefore most of what we think of as ordinary matter, is in fact empty space. So if this apple were the atomic nucleus, the electrons would be a kilometre away.
After discovering the nucleus, Rutherford continued doing experiments, firing particles at different targets to delve into the structure of the nucleus itself. By 1932, Rutherford and his colleague James Chadwick had found that the nucleus is made of 2 kinds of particles, positively charged protons and electrically neutral neutrons.
The discovery in these experiments of neutrons, uncharged atoms of mass 1, has proved of great significance and importance, and has given us a much clearer understanding of the actual structure of nuclei.
If you want to see more videos, search YouTube for Rutherford's gold foil experiments. There are some good videos of scientists that have recreated this classic experiment. All right, I hope you all enjoyed, and that was part 3, and I'll see you back again for part 4. So long.